Okay, so as a golden wrap to this beautiful week, Alexander.
Yeah, thank you for being here. Last talk of the conference. It's an honor to be here. I want to thank the organizers, Alessandra, of course, for also being part of her group in many ways for many years. I'm always welcomed in Amsterdam, and it's always great to be here. And then Apostolos and Giuseppe, of course, long-standing collaborators, but also Giuseppe, this is the best organized conference I've ever been to. Like, just perfect in all detail. Okay, so I will keep actually the category theory fairly light, and it will mostly be a Blackboard talk, but I have a few notes here. So let me say where do I start? Okay, so I want to say a few words about this phrase of mathematics engineering. So the reason I use this phrase is related to this program we have at Chapman University. So we have this doctoral program, Mathematics, Philosophy, and Physics. By the way, if you know a student who has a master's and would like to join us at Chapman for that doctoral program, the applications are open until mid-January, I think. And if Peter, of course, and I would be very happy to provide any details. Yeah, so one of the topics we are discussing there at the moment with kind of a subgroup of mathematicians and philosophers is kind of this question of convergence between mathematics and computer science. And in particular, what I'm interested in is the software engineering aspect. So there have always been this idea that theoretical computer science is part of mathematics, and it's a lot of philosophy of computer science in terms of like philosophy of computation, right? So that's has been a big topic for a long time, but that's not so much what I'm interested in. So I want to look at it from a software engineering point of view. And I think maybe the best paper to explain my interest here is the one I linked there by Comelin and Topaz. So they were involved with this liquid tensor experiment. I don't know whether you heard about that, but yeah, Peter Scholze initiated this. So kind of fields level mathematics, where he himself said, I don't understand my proof, it's too complicated, so let's implement it in Lean. And then it took the Lean community just like maybe half a year, I think, to nail the proof down. So and kind of two of the main people involved, Comelin and Topaz, wrote this paper about their experience. And it's really striking because if you read that paper, this is really software engineering, and they make this very explicit. So I pulled out a few phrases they use in the. So they talk about interfaces, they talk about tests with spec-driven development, mathematical debt in analogy to technological debt. They talk about refactoring dependency graphs. Obviously, they use version control systems. And yeah, so I think it's very interesting to think about this question. So on the one hand, it could just be that this is kind of what we always do in science, right? Using technology of a neighboring area, right? We can be mathematicians but use a calculator. That's a very superficial kind of interaction, right? So that could be one explanation. But you could also say maybe there's something really deeper going on, right? And actually, I think we've seen examples in the two talks today. It could be interesting our lunch to talk a bit more about that. For example, in Sebastian's talk, the way kind of the proof was organized was use similar principles as we organize software and software. But there's even another aspect, which is that all these logics have tools actually, right? So there's they're very interesting. I think this is a very interesting question. Anyway, so because this is on my mind anyway all the time now, because we have this kind of little project there. I also use this ideas for my own presentation today.
It's another obvious example is complexity management, right? Viewpoint extraction, modularization.
Yeah.
Abstraction.
Yeah. Okay, so let me now go more to the talk. So this is kind of a proof that you all know, I think. So we have equation logic and universal algebra, and there's this famous results that by Birkhoff that equation logic is complete for universal algebra, right? And so I will go through this in quite some detail. But so the main idea here is that I think that you all know this very well, maybe better than me. And sorry, could one switch off the light? Oh yeah, thank you.
But I mean, I think the problem is Alexander wants to use the ball.
Oh, okay.
So
Then we turn off.
yes, then I think it's better.
This is bad. Okay.
But then maybe it would be harder to see what is written on the board. This is why I
Can
think
you?
it's
Yeah.
hard.
I see. Okay.
Why? Yeah.
So if I write something here, can you see that?
I can turn on again when you.
Okay, it's no problem. I'm going to draw my.
No, no problem.
Like maybe with the if we open the blinds.
It comes with the role of the chair to control the lights. That's what.
Yeah, but I don't want you to read all of this right now. So this is my only slide. This will stay there during the talk. Just have well. The main idea of the talk is to take this proof and of completeness and to write it in a way that that we can change the things in red, right, to get new theorems for new logics, right? So that's kind of this software engineering methodology. In some ways, right? So we always refactor our software as mathematicians. We also refactor our proofs, right? So this is the same proof as in all the universal algebra textbooks. But when I look at the universal algebra textbook, it looks very different, right? And kind of my argument is that so it's in some ways the same proof, but it's the same proof only if you compile it kind of down to, I don't know if you compile, yeah, it's really but it's important if you kind of to get the level of abstraction right for your purpose, right? That's what we kind of to take something and refactor it so that it's at the right level of abstraction for what you want to do, right? So that's kind of one of the things they also emphasize in the Competent and Topper's papers. That is something that we always do both in mathematics and in software engineering. Okay. So why do I want to do that? So I've been actually, this has been kind of a little hobby for me for like 15 years now. I like to work with quantile enriched category theory. So this goes back to to joint work with Jirka from Prague. And originally it was the idea, so I've done a lot of work on modal logic and coalgebras. So so that's kind of beautiful category theory that allows you to do some work that we do in modal logic to generalize it and to do it on a more abstract level. And then can this be generalized to many value modal logics, right? And so basically what we need to do that is we need a way of doing many valued logics that slots nicely into the category theory, right? And so the right level of abstraction for us is the notion of a quantile. So we have a quantile Q. And so what is a quantile? I don't want to give a formal definition, but so it's a complete lattice, right? So a complete lattice of truth values. So we have infinite joins, and we have a multiplication. The multiplication could be the meat, but it doesn't have to be the meat. It can be something else. If it's the meat, then a quantile is just a complete Heyting algebra. But the multiplication gives us some extra structure that we can that we can exploit. So, for example, the most famous example is the real quantile. So we take the real numbers from 0 to infinity. We take it with a converse order. So 0 is top. So the idea is that 0 distance is true, right? So there's this double kind of way of looking at this quantile from a truth value point of view and from a distances point of view. And the confusing thing is that for distances, the order is the other way around than for truth values. So distance 0 means true and distance infinity means false. And so this is an example where you don't want the meat as your binary operation, but you want addition, right? So you want to be able to add the distances. So we actually should put, so you have addition, and then you have a neutral element, and then the neutral element is 0. So what is nice about this structure is that so-called quantile enriched categories now include metric spaces, right? So on the one hand, we can do many valued logics where the truth values are from a quantile. On the other hand, we get these additional structures, which are interesting. Like metric spaces are interesting structures. And kind of if you work in the framework of quantile enriched categories, you get kind of both for free and very nice general theory which connects the two worlds, many valued logic and kind of metric space and lots of other kind of structures, right? So I mean, this is just an example. If you choose this particular quantile, you get actually generalized metric spaces because distances don't need to be symmetric, which is also meaningful for some applications.
So infinite stays for the top element.
So 0 is the top element because we turn the order. And we need infinity because we want to be able to say that 2 points are not related. Yeah, so for example, we want to be able to do the coproduct of two metric spaces. We need infinity for that. Yeah.
I want to, because now in the recording we only see this and the video is not even existing. So I would like to ask if I could, but then how would I?
You can stop sharing. Stop sharing.
Yes, but then we won't see this. That's the problem.
But this slide will not change. It will be the same. So everybody can take a screenshot.
Yes,
and
okay.
the slide will not change.
because then maybe it's better to make this the main, because now we can see the, and we can also ah, yes, then I think it,
We can still see the slide. So if you move the window downwards,
oh,
yes.
this is brilliant. Okay, very good. Sorry for the interruption.
No, that's good. Thank you. Okay, so yeah, so what's the takeaway here? It's just this continuous category theory is for me the right way of kind of combining all these different areas into one body of mathematics, which is really very nice to work with. There's also kind of from an applied point of view, there's really a lot of interest in kind of quantitative logics, right? Not least Dexter Cozen and his colleagues have done a lot of very interesting work on quantitative algebra. And I have actually to apologize to you, Dexter, because I've not reviewed all that work. This is really something we still have to do. So my way of approaching it is really right. So I want to start from the category theory and see what I get. Right, and there's quite a lot of just groundwork to do, and I'm actually very grateful to Ivan, who was visiting at Chapman over the last 6 weeks or so. And finally, I have a collaborator who wants to work with me on this, right? So it's really, there's just a lot of infrastructure to create, right? So we have a framework where we have basic results about quantile enriched category theory. But then if you want to do model logic, universal algebra, all this stuff, kind of in this generality for all quantiles, there's a lot of basic results still to prove. So Ivan and I, we started just to look at, pick any result and see what do we need to prove in order to actually make it work in the quantile enriched setting. And this is one example. Right. So let's go through this. So let's see whether you can agree with me that this is a proof of completeness as you know it. Right, and then I explain what the changes are we need to make. So item 1 is a term algebra. So that's really completely classical, and it will also not change. It will we will use the same notion of signature as in the classical case, and also the term algebra will be the same as in the classical case. So then the second item is the definition, or what does it mean for an algebra to satisfy an equation in our case, right? So we start with equations. So this is really just an equation between two terms. I was looking for what's the best symbol to use here, and at the moment I like to use a theta for theory. But there's no assumption at the moment that these thetas, the set of equations, capital theta is closed on a. So this is just a set of equations, and this is an equation. Okay, so then what do we do with equations? We take quotients. So how do we do that? So really, this is here we we organize the equations into a diagram, right? And then we take a co-equalizer. So A, I write this as A quotiented by the equations. So there's a lot of kind of general results that already just follow from the universal property of a co-equalizer. So for example, that the class of equationally definable algebras has a free construction, has a free algebra, right? So that just follows from the universal property of a column. So one thing we're going to do when we generalize this to the quantile setting, we'll have to find, we have to say what are our new equations, and we have to say what is the corresponding notion of a column. So do I want to say more about how that works? So maybe just a little bit. So what is an equation, right? An equation is I can write it like this. So I have the term algebra. Let's just assume that we have a countably infinite set of variables. Right, so an equation is just a pair of terms, right? So I can write it as a parallel arrow, right? And then I also want to close it under substitutions. Right, so I take all homomorphisms from the term algebra into my algebra A, right? And now I have this, this is a parallel pair, and this parallel pair here up here is kind of the collection of all those, right? For all equations and for all homomorphisms, I kind of assemble them into this parallel pair, and then I take a co-equalizer. Okay, so the next bit of technology, I'm not sure how well known this is for people who work in universal algebra, but not from a category theoretical point of view. So it's the following idea. Maybe I can jump directly to item 5. So we said what a quotient is, right? And so I can take also a quotient of the term algebra, right? So let's do that. So we take a quotient of the term algebra with respect to my equations. And so now what does it mean for an algebra to satisfy the equations? So we can reformulate this by this factorization property, right? So with A satisfies the equations theta if and only for all homomorphisms like this we have a factorization. The definition of injective doesn't insist on this factorization to be unique, but in our case, so A in algebra A is injective with respect to this quotient if and only if A satisfies the equations. In our case, this factorization is unique because the quotient is surjective, right? So what's the upshot here is just that satisfying equations is categorically this injectivity property. So this is this also plays a big role in the proof of the HSP theorem. This becomes a very transparent short proof if you do it in terms of factorization systems and injectivity. So for us, certainly that looks like a good level of abstraction. Okay, and then the next observation here with respect to to completeness would be so that so now I'm going to item 6, right? So so I want to say that so for completeness, I want to talk about. Yeah, we only have we mostly actually we do have blackboards now at Chapman as well, right? But we used to have only whiteboards. So I need to get used to it is using top again. Okay, anyway, so completeness, right, is about everything that is semantically a consequence also needs to follow from our proof system. So how do we make the bridge of kind of semantic satisfiability? So we have this quotient here, right? And so this is the same as that theta is an element of the quotient. Okay, so now the next step is to learn more about this quotient, and that's also something we can do on a very general category theoretic level here. Is so the quotient is a colimit, right, and the kernel is a limit, right? So we can describe the kernel set theoretically as the set of pairs that get identified by the quotient. But we can also, in a more categorical manner, we can also say the kernel is just the pullback of the quotient morphism. And so we have this. Actually, we get from this kind of duality or Galois. So roughly speaking, we have relations and we have quotients, and we take a co-limit in this direction, and we take a limit in this direction. So the limit is the kernel, and the co-limit is the co-equalizer in our case. Talk about equation and logic. And so if I go around this way, right, so this gives me a closure operator here. And this closure operator is defined via the category theoretic properties of co-limit and limit. And via this injectivity property, we know that this is also the closure operator which characterizes semantic consequence. So that's kind of the way we use the category theory here. We define from the category theory we get this closure operator, and the way we set up this thing using the injectivity, we know that this closure operator is the one which corresponds to the semantic consequence. Okay, so. This is item number 8. So the semantic closure is limit after co-limit, or kernel after quotient after co-equalizer, right? And now the only thing that is remaining for completeness proof is to characterize this closure operator in a syntactic way using a proof system. So this is now kind of the template we can instantiate, right? So we need a notion, we need a kind of logic, we need a notion of co-limit, we need a notion of limit, and then we just engineer the proof system to match the semantic construction. And each time we do this, we get a completeness theorem. Okay, so what's the time? It's better look here. So how familiar does that look to you? Is that like, do you recognize the completeness proof of equational logic as you have seen? Or that look?
What can you do on the other side of the category with co-equations and like?
Yeah, what I can show you is for example in the quantile enriched case, what the logic is going to be.
This all dualize quite smoothly.
Oh, you mean, yeah, wait, what do you mean? I mean, I'm not, okay, so dualizing, I'm not dualizing anything here, but like when you say dualize, what do you have in mind?
I mean, at the other end of the category for like co-equations and.
Oh, okay. Yeah, so there's many, okay, so maybe there's some, so if I, okay, so not sure whether this is what you're thinking of when you say dualizing, but I always think of okay, so let's say I do some modal logic, right? So I have maybe some Boolean algebras plus some modal operators and some cryptic semantics. And then I have a dual adjunction between sets and Boolean algebras. And then I do some coalgebra stuff here and some algebra stuff here. So currently I'm just talking about this side of things here. So if you're asking what happens here, that's interesting. But yeah, I mean there are lots of question marks, and I'm happy to talk about this. Yeah. So yeah. Okay, let's think about what should happen in the case of quantile enriched universal algebra, or maybe we can also think about metric spaces in particular. So there's a fundamental result about quantile enriched categories, which is the following. So what is a quantile enriched category? Essentially, it's just a set A together with a mapping into the quantile, right? So if you take the quantile to be the real numbers, then this is the distance function, and the actions of a category make sure that this respects the triangle inequality, for example, right? So a quantile enriched category is just the set A together with a distance. Let's stop with that. That's a good way of understanding. Okay, and a fundamental result about quantile enriched categories is that one can represent them as relational presheets. And so there's an adjunction here. And this adjunction is actually familiar also from the theory of metric spaces. And essentially the idea is you can describe a metric space also by a family of relations which are indexed by real numbers, right? And the idea is that you go to each metric space, you associate a family of relations indexed by, I write now Q, right? Because my distances are elements of my quantile. So essentially what you want to say is you want to collect all pairs which are kind of closer than epsilon. So what you normally would write smaller equal to epsilon, right? And this would be the epsilon. And makes sense, right? So you can it's pretty intuitive that this is the same information as a metric space. If you know for all 2 points, for every epsilon, you have a relation which collects all points which are closer than epsilon, right? So it encodes the same information. So let me just rewrite this a little bit. So now I want to call it Q, right? And then I also call it this. We also use the same letter for the function as for the underlying set. That's traditional in category theory. So I can't avoid doing that. So the hom, so to speak, right, from A to A prime is now not a set, it's a number, in the quantile, it's an element of the quantile. And we just say that this must be greater or equal to Q. So I use this square inequality thing for the special for the order of the quantile, right? Just to make sure that I always know when I'm referring to the order of in the quantile. And the order comes kind of around, right? Smaller or equal to epsilon means above epsilon in the order which corresponds to the truth values, right? So this is very confusing. But this means, think of this as smaller or equal to an epsilon. Okay, so now there are, you need some actions on these relations to make sure that they exactly correspond to a metric space, right? So now they are just relations. So there's a theorem here which says, like, what are the actions which make this actually an equivalence, right? So again, so maybe I should reproduce this picture, because that's not a coincidence, these two pictures. This picture is the one this is the picture I plug in here to get the completeness theorem for quantile enriched universal algebra, right? So all I need to do is I need to know what this closure operator is, right? So this is which relational presheaves are exactly quantile enriched categories. And that's a well-known result in the literature. So what they call this is a Lux monoidal functor, but it's just how category theorists like to call it. Okay, so maybe it actually works well, because that's pretty much the last thing I want to say. So let me see if I can fit this. So I want to now explicitly describe what this clone is, right? Right. So this will give me the syntactic closure I need for my completeness, which I need for my completeness here, right? And you can just plug this from the literature, right? So this is in an old paper by Kimi Rosenthal. He's one of the researchers who worked a lot on quantile and quantile enriched category theory. And so it works like this. So it's a functor, so which means it has to respect the order. And actually, let me write it. It's kind of nice to write it in kind of more logical notation. So I call these relations here now turnstile sub q, or you could write less or equal sub q. So these are these relations here. But it looks like more like logic if I write it like this. So actually, maybe it's better to write it like this. So if I have t, I'm still making a mess of it. Right, so these turnstiles indexed by elements of the quantile, they correspond to my equations from before, right? Instead of writing t equals t prime, I write now t less equal t prime indexed by an element of the quantile. This comes directly from here, right? And now I just have to make sure that I get the contravariance right. So it should be contravariant. So if I put a prime here, I think it's good. So that would be now one of the rules that I have in my equational logic, right? So I will still have reflexivity. I will still, oh no, actually reflexivity will also see changes. I will still have the substitution rule and the congruence rule, but reflexivity, transitivity change, symmetry goes away. And instead of reflexivity and transitivity, I have the four rules or equations, rules maybe better to say, which come from this result that is saying that as they are called continuous relational precies are equivalent to quantile enriched categories. Okay, so the first condition we had on the relations, remember that this is now my cube here, right? Just change location. It's really about these relations, right? Okay, so a quantile has a neutral element. So let's call it 1 now more generally. It's what the 0 was before. I want to say that the identity relation is contained in the relation that corresponds to the identity of the quantile. So that replaces reflexivity. Or it is reflexivity if you want. And then for transitivity, you get that you use the multiplication on the turnstile of the quantile to get the right notion of generalized transitivity. Right. So okay, so now we need one more thing. It's called a continuous relational precis. So there's one more condition, and it has to do with the joints of the quantile. So quantile fundamentally has infinite joints, so I have to see whether I can remember this. So I should have put this explicitly in my notes because I always forget which way around that goes. So let's try to think about it. So actually, this was a functor. This is called Lux monoidal, right? Because it's kind of saying that this is the monoid, that these precies interact nicely with the monoid structure of the quantile. And so I want to say something about, okay, so I have lots of Q's here, right? So I have so the Q's run now over some set of indices. And then I want to take the join. So maybe I could use a square join over all these indices. So in terms of remember in terms of metric spaces, the join is kind of the inf, right? So it gives you the continuity you need in order to if you have an argument where you know something about for all epsilons great up to a certain limit, you can take the limit, right? So it's yeah, and so so kind of that's it, right? So I thought it was really beautiful to see that kind of if you write down the proof in all details, it goes over many pages. But most of it is really boilerplate. Most of it is exactly the same as in the classical proof. If you're just careful enough to kind of arrange the puzzle pieces in the right way. Yeah.
Yes, I guess that if you want to give a rule presentation, then identity including in R1 should be binarized.
Yeah.
With value E where E is your user.
Yeah, you're absolutely right. I'm mixing two different ways of saying the same thing. Yeah, so I should just say
This is your answer.
that T turnstile 1 T.
Yes.
Yes, you're absolutely right. Yeah, thanks. This looks like less like specifying a Lux monoidal functor, right? So, but it's really just this looks more like logic. And the other comes from the way of just writing down what a Lux monoidal functor is. Yeah, thanks. Yeah, that's also all I wanted to say. Thank you.
Questions? Yes, thank you very much, Alex, for this beautiful talk. Well, now you have, weighted, can you expand a little bit on some intuition about these weighted turnstiles? So we now say
You mean like this?
yes. So we not all of them. Now instead of saying that the sequence is derivable, we are saying that the sequence is derivable up to an extent. Is this?
Do you say symmetry?
No, instead of saying that the sequence is derivable, now we are saying that the sequence is derivable up to an extent. So we have these labels in the sequence. Can you expand on this?
Yeah. So my intuition is that another way to read it. This is T is less equal to T prime up to a Q. So it's not actually less equal. Like we're making a mistake here, and the Q is keeping track of the mistakes. And if the way you measure your mistakes is by addition, it's kind of this is a natural way of doing it, right? So you are adding. This is giving you an upper bound on the mistake you're making, if you right. Yeah.
Okay, thanks.
I don't have a question, but I just wanted to clarify that thanks for the shout out earlier, but I'm actually not involved in quantitative equation work.
Okay. But you do collaborate with Radu and Akash on some of the.
And I refereed their paper, but don't tell them that. It's Sanagat, Plotkin, Mardari, and Bakshi.
Okay. But you've done some work also on duality with them, right?
Oh yes.
Yeah.
But not.
Okay. Yeah. Yeah, so I didn't, as I apologize, I didn't review all that work. It's on my to-do list. But I can pay your. I can do. As I said, I'm just doing the stupid thing here, right? So I take my math and see what happens when I just unroll when I do the natural thing, basically. Yeah.
More questions?
Sure. There are other enriched categories. It's not always quantiles that you enrich with. So could this help?
Yeah, that's very, very good question. Yeah, so so this methodology always works when you have kind of this an adjunction like this, which gives you like this coordinate level, and like if you, you might even be able to do something where this is not a Galois connection but a proper kind of adjunction. If it's an adjunction sets of a Galois connection where these categories are actually posets, then you immediately get a completeness result in just by following this pattern. When you do it more generally, so where the categories you enrich over are not posetal, but like kind of, so to speak, proper categories, then things get obviously much more complicated. And I don't know what I mean. That's something I also want to look into. Yeah, this is a bit like, I mean, for example, we call this the nerve of the quantile enriched category, and the nerve is a concept that is very important in, so to speak, proper enriched category theory in algebraic topology and so on. So there's a lot of so this is kind of like this is a post-Heckel version of the famous nerve realization adjunction from algebraic topology. So there's some interesting things one can think about, but then you don't get an obvious application to logic anymore, because kind of logic is about theories and classes of models which are contained in each other. So just the post-Heckel kind of setting. Yeah.
Just to maybe specify Peter's question, because for the canonical extension paper, one of the reviewers said, "Oh, why not quantaloids? Why not?"
Oh, quantaloids are not a problem.
Would this construction work?
No. Quantaloids are, because the homes are still post-Heckel. That's what makes things simpler. So if you go from quantiles to quantaloids, all you're doing is a quantile, so to speak, a one-object quantaloid. So you're just kind of making a typed version, a multi-type version of this untyped version, and that's just a little bit more notation, but it works. It works in the same way. Yeah.
Last chance to ask a question, Lisan.
So if I understand it correctly, the quantaloids are the quantiles, or groupoids are two groups.
Yeah.
Okay, so
And categories are to monoids, etc.
okay, but so I mean there are, let's say, sheaf theoretic representations for those, and I was wondering that whether, I mean, like that could kind of help the generalization. I mean, like, did you see any connection? Like now, you know, I'm just I'm completely speculating, but.
And that's do you refer to this famous paper by Wolters where he represents sheaves using quantaloids? Yeah, so that's an interesting construction, and I actually looked at it a few weeks ago, but
I was also thinking of Pedro Resendes work on representation of groupoid quantiles.
Yeah, I don't know. I mean,
Okay, but it's nice because I mean, 100 years ago I wasn't interested in this stuff, so it'd be nice to
yeah.
Maybe once, twice. I think it would be nice if Alexander and Giuseppe, if you say some final words to wrap up the. Let's thank Alexander again.
Yeah, thank you.
So, would you like to say some final words, Alexander, to wrap up the?
typically is the chair of the last session.
I can say something.
It's all fun.
Okay, so from my side, I have to thank you both for, it's been an immense pleasure to be part of all this. I think you are running a family. And after, a week of all these interesting talks and interesting conversations throughout the week and the build up of the different PhD theses, you made me at least to feel almost part of the family as an admiring distant relative at least. So thank you very much for that and thank you all.
Well, I definitely then am obliged to respond. I mean, like, you have to be part of our family. And I mean, I was thinking of what Dexter said. I mean, like, it looks like they are my kids too, right? I mean, like, the kids. And so, yes, it's definitely been at its finest. So I thank you all.
Should we do it now or?
Yeah, I.
Let's do it.
Yeah.
Okay, I have something important to say, everyone. So please pay attention. Okay. So yesterday evening, Krishna said some beautiful words about our logic family. I am not as good as him. I cannot replicate the speech, but I need to add something because unfortunately Giuseppe was a little bit under the weather, and he also deserves to be acclaimed as one of the best organizers ever. And for this reason, we have a present for him. He will receive a card. We know that he loves movies, and this is why he now has a movie card gift for 6 months of movies for free in the Netherlands. I will give him the code later, so he can play the.
And now just some practical final things. First of all, I'm making we made a Google Drive folder. We will share with you at your email and also in the WhatsApp group. So if you have pictures of these days, please put them there, and then we can share them. And finally, this afternoon we have
slides there.
Yes, we
will put the slides as well. Yes, but also I think we'll put on the website with links to the videos.
At 5 there will be a wine and cheese party at the Van Breestraat 131. You are all invited, so I hope that to see you all there, including you. Yes, I mean, you were one of the speakers. I mean, we need
Yes. But I don't know what